Next time you fly through a storm, look out the window. You'll see the aircraft's wings flex under the massive aerodynamic strain of turbulence. In the cabin, a wing appears as a solid, unyielding block of metal. Beneath the surface, we find a different reality, a hollow cavity supported by a thin-walled lattice. Modern aircraft rely on semi-monocoque construction. This eggshell-like design uses a vast, mostly empty space, reinforced by a fragile-looking framework of thin metal ribs, stringers, and webs. This empty space is constantly subjected to massive vertical loads. When turbulence hits, an immense external shear force strikes directly across this delicate internal skeleton. Engineers must ensure these metal walls, some only fractions of an inch thick, can survive thousands of pounds of tearing force without snapping. The solution lies in how energy is forced to move through the shape of the metal. Let's pull a single C-channel support beam out of that wing lattice and look at its cross-section in microscopic detail. Because the metal wall here is so thin, the shear stress trying to slice through it has no room to vary from the inner edge to the outer. The stress remains completely uniform across the entire thickness of the metal. Engineers use the shear flow equation to calculate Q by multiplying uniform shear stress by the metal wall's thickness. This equation traces a fluid-like current, transforming static stress into a calculable river of force moving along the beam's perimeter. Treating stress like a fluid allows designers to predict exactly how destructive energy will travel through the geometry of the part, identifying points of failure before the metal is even cast. This diagram shows the exact shear flow distribution in our C-channel. As the force enters the top horizontal flange, it follows a specific geometric path. The triangular graph on the top flange shows the buildup. At the open outer edge, the shear flow is zero. It builds in a perfect linear slope as the energy moves inward. The flow then turns the 90-degree corner and enters the vertical web, accelerating as it carries the accumulated force. In the web, the distribution forms a parabolic curve. The intensity of the force swells, reaching its maximum at the neutral axis, the center line where the beam experiences zero bending stress. The physical shape of the beam acts as a literal channel, forcing invisible energy into these precise, predictable geometric patterns. Stepping back to look at the whole cross-section, we can see the total forces, or resultants, operating simultaneously. The flow flowing through the top flange creates a horizontal push to the left, while the bottom flange creates an equal horizontal pull to the right. These horizontal forces are identical in magnitude, but point in opposite directions, meaning they mathematically cancel each other out entirely. This leaves the massive vertical force concentrated in the web. This internal upward flow acts to perfectly counter the original downward load pushing on the wing. Static equilibrium is an active, dynamic state. It is the result of massive opposing currents of energy neutralizing one another within the metal. This balance remains fragile. If the external load from the wing is applied even slightly off-center, it fails to align with internal forces. Engineers solve this by locating the shear center, the precise mathematical coordinate where a load must pass to ensure the beam bends without twisting. Missing this center creates an unbalanced torque, violently twisting the thin-walled metal like a wet towel, leading to structural failure. Every rib and stringer in a modern wing is mapped to ensure these aerodynamic loads align perfectly, even in the most extreme conditions. Modern aviation relies on these perfectly balanced internal currents, turning empty shells into structures capable of mastering the immense physical pressures of the sky.